Hi, my name is Charles Kawasaki and I worked on this project with my teammates Ajay Raddy, Hannah Getty, and Austin Lanu. Our project is upgrading wildfire-resistant shelters with a superabsorbent polymer layer. In 2020, California wildfires alone destroyed 10,500 structures and killed 33 people. Current fire shelters are expensive and don't offer a guarantee of both safety and survival. This project aims to implement a layer of superabsorbent polymer into a fire shelter to guarantee the safety of the individual or belongings they may leave behind for an affordable price.
For these fireproof shelters, current market standards consist of one layer of aluminum foil that is backed by woven silica. This one layer functions as a fire repellent and heat barrier. In the image on the left, you can see a wildland firefighter demonstrating what one of these shelters look like in action. And on the right is an image of one of these layers cut in half. As you can see two different layers of aluminum foil that is backed by woven silica.
As part of an in-depth market analysis done on the current products, we actually found that there were numerous drawbacks of such designs. Some of these include that they actually started falling apart at a very low temperature of just 260 degrees Celsius. This was due to poor construction and material choice. Many of these designs also have very cumbersome deployment methods, which is extremely unideal given the use case of these products.
Our team is introducing superabsorbent polymer, or SAP, as a solution to these issues. SAP is a white powder that can absorb over 100 times its own weight in water within 2 minutes. You may not have heard of it, but you've definitely used it. It's what soaks up the pee in diapers, and is also used for some cold packs and helps solidify medical waste.
With the new fire shelter that utilizes the current market standard layer but is backed by SAP, the temperature within the shelter is decreased by about 97%.
When it came to designing the shelter, an important design factor we had to consider was how much water was required to achieve a minimum thickness that would provide the maximum protection against a fire. In previous tests, thermocouples were strategically placed in a prototype containing SAP in order to accurately measure how much heat was able to pass through the barrier. These tests concluded that 1.5 centimeters was the minimum thickness needed to protect someone from hyperthermia. In a real forest fire, we cannot ensure the user will have the ideal type of water to hydrate the SAP, and hence we conducted absorbance tests with DI water, tap water, and salt water in order to study how SAP would react when hydrated with various sources of water. The salt water was meant to simulate the use of urine to hydrate the prototype. Each prototype was filled with excess SAP and hydrated with water. Thicknesses were measured after each addition of 50 milliliters of the liquid. And if I may direct your attention to the graph on the right, you can see the DI water and tap water results follow similar trends, showing that about 125 milliliters of water per 4x4 inch prototype, or 1.2 liters per square foot, is needed to achieve the minimum effective thickness. These tests also proved that salt water is not an effective way to hydrate the prototype.
So as you can see by now, this technology has some serious life-saving potential, and we feel that the best and quickest way to get this into the hands of the consumers would be to release the product in 3 stages, each one more advanced and focused than the previous. Phase 1 would include small-scale property and personal protection for the population living within high-risk zones. Phase 2 would include specialized personal protection geared towards outdoor enthusiasts. And lastly, we have Phase 3, which would include ready-to-go shelters scattered throughout the high-risk zones for anyone and everyone unfortunate enough to be caught in a forest fire.
There's still work to be done in the lab, too. Many fire-resistant materials are characterized using the metric of thermal protective performance, or TPP. With the purchase of a copper calorimeter, future tests can be conducted to get a better estimate of our shelter's capabilities. These tests would also allow for direct comparisons to competitors. Thanks for listening. Please stop by our room if you have more questions.